Hi, this is Professor David Farina. In today's lecture, we're going to be talking about the solar system and, in particular, interplanetary matter. Let's get started. So, what does interplanetary mean? It means the stuff between the planets. And you guessed it, space is not empty. We've got a lot of stuff in space, and one of those interplanetary matter things could be asteroids. So, of course, you have heard of the asteroid belt, but the asteroid belt is just one pocket of asteroids. There's also the Trojan asteroids as well, which are much farther out. And we also have other debris out even farther, which we're going to talk about in later slides here. So you can see that some of these are also Earth-crossing asteroids. These, of course, are the ones that are most notable in terms of things like mass extinction events in the past, and possibly a Hollywood movie similar to Armageddon or Deep Impact, where we are discussing the possibility of life on Earth currently being affected by one of these space-based bodies. Some scary stuff, but nonetheless, we need to be aware of it, and the only way to learn more is to monitor and observe, and asteroids are something of vast interest to scientists and Hollywood and maybe the everyday person. Maybe you. So, how do we look for comets and how do we look for asteroids? What we do is we monitor the sky and we find what's different between two sets of images. Now, you might see an asteroid move through your field of view in a telescope, similar to this picture that was taken as the object moved and the camera was taking a long exposure. The asteroid made a streak in the camera's imaging path, and we can now look at that and determine, we know how long it was moving, we have an exposure time, in other words, and we can then figure out, well, how long would this be, and we can figure out its speed and possibly its orbital path, or even determine where it might be now so that we can monitor it further. Now, you can see here in this image, we've got various different sizes involved. So we've got this one, Ida, and its moon, Dactyl. Yes, asteroids can even have moons. There's Ida, and right there, tiny little Dactyl. This is a 30-kilometer across body of material. Here we've got another comet, or another asteroid, I apologize. This one, once again, 30 kilometers to here, a little bit bigger, maybe about 60 kilometers across. And this one's much, much, much smaller, only 250 meters in this part of the image. So remember, about 100 meters is the one football field with the end zones included. So, I don't know, this might be about 10 football fields or so long from one end to the other. So significantly smaller than these, which are city-sized objects. Now, one of the things you may have heard of before is that an asteroid possibly killed the dinosaurs. So, what type of statistical probability do we have to have a similar thing happen today? Well, this is kind of an interesting question. An annual event could occur where we have something about 5 kilotons. Now, a kiloton is 1,000 tons of TNT exploding. So 5,000 tons of TNT exploding. We have an event like that every single year. Tunguska, a once in a millennium, once every 1,000 years, where we have what is basically, a large amount of TNT exploding, somewhere in the order of 50 or so kilotons. And this one was enough to wipe out a large portion of trees. It's basically like a small nuclear blast at Tunguska. Now, this global catastrophe threshold here, this is where we start to get into the type of impactor where a global effect is occurring, where we have the impactor hits and creates what we would consider to be like a nuclear winter, where the clouds of dust and material that are blown up by the impact itself actually block out the sun. And when the sun is blocked out, of course, photosynthesis cannot take place, so plants start to die. The plant-eating animals on Earth will start to starve. As they start to die off, all of the meat-eating animals that are on Earth also start to die off. And so this happens both on land as well as in the ocean. And this has happened in the past on multiple occasions. We call those mass extinction events. Now, not all of them were caused by asteroid impacts. Some of them we think may have been caused by large volcanic eruptions or other events. But nonetheless, we think the dinosaurs were killed by a very large asteroid or comet. And you can see here on the scale of the megatons of TNT, the dinosaurs were very high up on this scale. And we think it may be a once every few tens and maybe even 100 million years or so for something like this to occur, fortunately. Now, when we start to view other objects, like comets, for instance, comets are made of some more icy material, and the comets are coming generally from farther out, where the sun is not very bright, and as a result, the temperatures are very, very cold, and the icy crust of these comets are able to form. But the comets are on these very highly elliptical orbits, as you can see here, and as they come in closer and closer and closer to the sun, they start to produce what's called a tail. Now, the tails are inclusive of material that's blowing off, as well as an ion tail. So there's two types of tail. The ion tail, you'll notice, always faces away from the sun. It's this bluer one here. Okay, it's actually coming in from this direction. So notice there's the ion tail. The dust tail starts to form here is actually material itself. So the ion tail is ions, which are charged particles, whereas the dust tail is actually matter flying off. Okay, this is an important distinction because you'll notice that the dust tail actually does lag behind a little bit, whereas the ion tail always faces away from the sun. So if this thing is moving in this direction, notice that the ion tail can actually be towards the front of it. It's kind of counterintuitive. In other words, it's flying into its tail. The tail does not always go behind it. Sometimes we can even get some jets that are flying off of the comets if the material is being heated up or sublimated so quickly. Sublimation, by the way, is going from a solid directly to a gas. And so if the material is being heated up sufficiently quickly, it will sublimate, and then that gas needs a place to escape. And if it's escaping through cracks and crevices on the comet, it will blow off in these jets. The cometary orbits are from pretty much all over the place, and you'll see them coming from this place which we believe is called the Oort cloud. Now, I say believe, that's because we only have evidence of the Oort cloud from things coming towards us, towards the inner solar system. We don't actually have images of these objects. They're extremely small and they're extremely far out there. So for us to see them, they need to come to us. The Oort cloud is thought to be the farthest extent of things within our solar system. Now, the Kuiper belt we talked about a little bit earlier is a component that is a disc-shaped object, and it's embedded inside the Oort cloud. The Oort cloud, on the other hand, is in 360 degrees, an entire sphere around our sun and our solar system. Meteor showers are actually associated with comets. Now, a lot of people don't realize that this is the fact. So you can think of like driving down the road, and you're driving through a snowstorm, and as you're driving through the snowstorm, you are seeing material which is hitting your snow, hitting your front windshield. So a meteor shower is kind of like that, where the Earth is flying through a debris field that was left behind by a comet. So as the comet comes through, Earth flies through it in its orbit, and each year as we enter this place in Earth's orbit, we return right back through that debris field made by the comet again, and the material hits the Earth's atmosphere, kind of like snow hitting a windshield. And it always comes from one particular direction. And by direction, I mean a particular constellation. And that's why we have a meteor shower named after a constellation, like the Orionids meteor shower, or the Perseids meteor shower. Those are the direction from which it appears the meteors are coming from. However, these meteors are simply comet dust that we're flying through. Now, meteors and meteoroids can be very small. They can just be a few millimeters in size, or even micrometers. They're just little dust grains, but when they're traveling at 30,000 miles per hour or more, it's very, very possible that you're going to see them fly through the night sky, and they burn up, they create a plasma, they actually heat up the air around them. To just give you a sense here, bullets might fly at about 1,000 miles per hour or so, where this thing is moving at 30 or 40,000 miles per hour. So significantly faster than a speeding bullet. And this, of course, is what people consider to be shooting stars. They're actually just dust grains from comet dust. Now, interplanetary matter can actually be seen around other stars as well. We see evidence of this, and we've taken images of it as well. We see evidence of impacts in Earth's past. Here is Barringer meteor crater in Arizona. It is huge, over 1 kilometer across. Here's another impact in Quebec. It's actually filled with water. So I hope you enjoyed today's video and you learned a little bit more about interplanetary matter. If you like this video, please click the like button and subscribe if you'd like to hear more. Also hit that bell at the bottom to get a notification each time I make a video. Thanks again. Hope you liked the video and have a great rest of your day.